Usually when I'm live with people, I ask the question, how many people believe there is some kind of life? And by some kind of life, we're not meaning necessarily intelligent life. It could be anything from microbes to algae to one-celled animals, all the way up to complex life. But how many people believe there is life somewhere else in this universe? And almost everybody raises their hands. And then I say, how about in this galaxy? Is there life elsewhere in this galaxy, in the Milky Way galaxy? And again, most people keep their hands up. And then I say, how many people believe there is life right now somewhere else in this solar system? And most people put their hands down. I can't tell you for sure, but I think by the end of the talk, you'll be convinced as I am that probably within the next 20 years, we will find life somewhere else. So humankind's primary question is, are we alone in the universe? And we're talking about intelligent life on the one hand. Of course, that would be the ultimate goal, but any type of life would be a monumental finding and probably one of the most amazing findings humankind has ever had. So when we talk about intelligent life, we're not necessarily talking about Avatar or some other sci-fi type of thing. They could look like that, but that's not really what we mean. So how do we look for intelligent life? Basically, we're looking for evidence of intelligence. And this is through SETI, the Search for Extraterrestrial Intelligence. And basically, radio telescopes are looking for repeated signals or signals in patterns. That would indicate that there is some kind of intelligence there. Unfortunately, so far, we have no positive findings. Some people are advocating doing other types of searches for intelligent life. For example, if you see a planet on a distant star and see what looks like artificial light at the night side of the planet, that would indicate intelligence, something along those lines. And so there are other ways of searching, and they're beginning to do that. So we can't answer the question yet if there's life elsewhere, because we have no direct evidence of it. But we are seeking things like some biological signatures. And what we mean by that is evidence of carbon dioxide, but especially of oxygen. And what happened? Sorry. Evidence of carbon dioxide or oxygen, especially oxygen, or evidence of other organic molecules. And I'll talk about that as we go along. In the meantime, though, we can also look for habitability, meaning is there a habitat on a certain planet or moon that indicates there's a possibility of life. And there's three necessities. You need to have persistent liquid, mostly water, but other liquids could suffice. Key chemical ingredients of life, and that we mean both atoms and molecules, like potassium, sodium, carbon, oxygen, hydrogen, etc., as well as more complex carbon molecules. And you need energy for metabolism. Every organism that is alive has to have some kind of outside energy source. So basically, we've been looking in two areas. The first one is in distant stars, not the stars themselves, but exoplanets, that is, planets around a distant star. And we've also been looking in our own solar system at some planets and moons. So just to give you a hint about, the possibilities in terms of distant stars, there are probably, this is an underestimation. It says 100 billion galaxies in the universe. They're now thinking it's more up to 1 trillion or so. And our Milky Way is an average galaxy, and there's about 300 billion stars in the Milky Way. And so there are more than 3 times 10 to the 22nd power stars in the universe. Just to give you an idea of that, so it would be 3 times 10 with 22 zeros after it. That's more than all the grains of sand on Earth put together. So there's really a good possibility of life elsewhere. And so far, we've discovered 5,500 exoplanets that have been nearby, and I'll tell you how we were able to do that. The planets themselves were detected sometimes by radio velocity, oftentimes by transit, and sometimes now with the James Webb Space Telescope by direct imaging. So the way radio velocity works is it gives us a Doppler shift. As the planet goes around around the star, it tugs on it, and the star wobbles, and that gives us a Doppler shift, and we can tell that there's a planet. The only thing it does is it gives us the planet's location and mass, but there's nothing about its atmosphere, which is a lot of what we want. And you can see this this planet going around the star, and as it tugs on it, it wobbles, and we can tell there's a shift in the Doppler as that happens. Transits are better because they measure change in brightness as the planet passes in front or behind its host star. At best, though, the dip is only about 1%, but we have telescopes now that are sensitive enough to detect that. So it not only gives us information about how big the planet is, but we can study a planet's atmosphere using spectrography. And again, you'll see in a minute, as this planet goes around the star, you'll see it go in front of the star, and that causes a little dip in the star's brightness. So NASA has a satellite up called the NASA's Transiting Exoplanet Survey Satellite, or TESS. And this has very sensitive telescopes able to detect the brightness of a star, and when it dips, it's able to see that there's a planet there, and also look at the planet in terms of what kinds of atmosphere it has. But you see that the dip that occurs going from 100% goes down to only 0.03% of a dip. So that's not even a 1% dip, but they are able to see it. So one of the ways we really wanted to be able to take a look at exoplanets was with direct imaging. That is taking actually a photograph of these exoplanets. The problem is, seeing the planet, you're seeing it through the glare of its host star. So if you take this sun-like star, it's just like the sun, and a hot exojupiter, meaning it's very large like Jupiter, but it's hot, so it does give off its own light. It's still 1 million times fainter than the star itself. When you get to the Earth-like planet, which is smaller and colder, it's 10 billion times fainter than the star. So it'd be like the star is like a lighthouse. The comparison is trying to find a firefly flying near the lighthouse, or trying to find bioluminescent algae flying, near the lighthouse. So it's very, very difficult. But NASA has accomplished it. And the way they do that is there's a coronagraph, which basically blocks the light of the sun. And so what you see is anything glowing around it. And you can see there's 1, 2, 3, 4 planets around this star. So now what? We've discovered over 5,500 exoplanets. The next thing is to think about how do we go from planet detection to planet characterization. And the things we want to know is, does it have an atmosphere? What molecules are present in the atmosphere? Because that's important. That'll give us a hint whether there's actually life. Could it support life? Is it in a habitable zone? And finally, does it have life? And that question has yet to be answered. So when you're looking for habitability, you look sort of where the planet is, in what zone it is around the star. If it's too close to the sun or to the star, the surface would be too hot. Too distant, and the surface has no liquid water. There is an exception to this that I'll talk about later. There are several hundred planets that are found in the habitable zone. Some actually had signature gases like carbon dioxide. There was one planet found with carbon dioxide, none so far with oxygen. So these are the different zones. And you see if the star is hotter, this is a very blue-white star, that would be in one of the higher classifications, and so much more hot. The habitable zone then is further out. If it's of a red dwarf, let's say, and so much cooler, the habitable zone will be closer. Our sun is an average yellow star with average heat, and therefore it has a habitable zone all its own right around here. And just to give you an idea of the comparisons, if you look at our solar system, Mercury is too far in to be in the habitable zone. Mars is just on the very edge of the habitable zone. Both Venus and Earth are in the habitable zone. Venus, however, because of its tremendous cloud cover, is very hot on the surface. We'll talk about that later. But if you look at the TRAPPIST system, where there's a red star, that habitable zone extends pretty far. And so there's about 4 planets that are in the habitable zone. The Hubble Space Telescope actually has been able to find water vapor on 30 different exoplanets. The problem is these planets are all in the hot zone, so they're too hot to have liquid water on the surface. And now we have the James Webb Telescope, which also has been looking for exoplanets and has found several. How do we look for life? Well, especially if you find oxygen, it means there is plant life in the planet, because that's how oxygen is generated. It's plants and algae that generate the oxygen. You can analyze the reflected light from the planet to see if it has an atmosphere. We can try to look for liquid water, and I will talk about that in a minute. And we look for signs of biological activity like methane and other evidence of biological activity. Methane does occur naturally as well, but if you have a prevalence of methane, it could be biologic. Well, it just so happens that there's a new finding. This was found by James Webb Space Telescope, a planet called K2-18b. It orbits around K2-18, the star. It's 120 light years from Earth. It's in the habitable zone of a star. It has liquid water besides a dense atmosphere. And that dense atmosphere is mostly carbon dioxide and methane. But that doesn't deter us. One of the amazing things is there's a possible detection of dimethyl sulfide. in the atmosphere. It needs to be investigated a little more. But if that's confirmed, at least on Earth, the only time we find dimethyl sulfide is as a metabolite of algae, marine algae, phytoplankton, or bacteria. And that's what gives the ocean its fishy smell. So that if we confirm this, is a pretty, I wouldn't say definite, but pretty good likelihood that K2-18b does harbor life. Now, what about solar system investigations? There's possible evidence of some previous ancient life on Mars, or at least the habitability of it. There's evidence of some habitability in other bodies that I'll talk about, but no evidence of actual life yet, although we're seeking it. On Mars, early rovers had the suggestion of water because it looked like there were outflow channels and layers of rock. And then when we landed Curiosity on Mars, it confirmed the presence of water. It was present for about 1 billion years until maybe 3.6 billion years ago. And this was around the Gale crater. And Perseverance confirmed the evidence of water as well around the Jezero crater. So if you look at Curiosity's findings, the surface all around the landing site were made of these pebbles. All were sedimentary, and there were sedimentary layers around it. Many of the pebbles and rocks were rounded, and the only way of doing that would be through erosion due to liquid water. And further away still, there was extensive sedimentary rock that was seen. The spectrometer on Curiosity also found that the water that had been present, it was none on the surface anymore, but what was there was low in salinity and had a neutral pH. And therefore it had a habitable environment, was relatively young, but had enough time to be able to form life. We now think that life formed on the Earth only 400 million years after the Earth was formed. We used to think it took a couple of billion years, but not any longer. So this would have been enough time to have formed life on Mars. The other findings were that the spectrometer noted that there were building blocks of life. Again, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. And some complex carbon-based molecules were present. And especially with the carbon-based organic molecules, it could mean two things. Some of these can happen naturally. We'll get to that. But it might have been biologic in origin, meaning ancient life. And this is the area where it was looking at, and you can see all of this sedimentary rock, meaning that Mars had water on its surface for a prolonged period of time. And these are these rounded pebbles, and you only see that in a fast-moving stream. Perseverance also landed on Mars in February of 2021 at the Jezero crater, another crater. And this location was a river outflow channel and delta. And it's the best place to look for ancient life because of the fact that as the river goes down and reaches the outflow channel, it slows, and all of the material it brought down from the higher elevations are deposited. And that would include life if it was present. And so Perseverance has been drilling for core samples around this crater and has stored them in titanium tubes. So these are some of the eroded stones. You see that they basically look like they're sedimentary, sort of a conglomerate, but also smoother, so eroded. And this is the kind of stuff that's all around it. So there's going to be a future mission, hopefully, if NASA, if Congress decides to fund it, and keep the fingers crossed. Perseverance, as I said, is collecting core samples. What's planned is that in the 2030s, a return mission would bring those samples back to Earth. There's a lander that will land next to Perseverance. It would obtain the samples that had been collected and return them to Earth for study. The plan is to determine if these organic molecules that were found are biologic, and that would be an indication of ancient life. And so the way it works is, this is Perseverance. It has collected these titanium tubes and stored them on board. It will go over to the lander, and this is the sample return lander. And you see one of the tubes in its arm that would be put inside into a container. The rocket would launch from the sample return lander, dock with the Earth return vehicle, and this would return to Earth with the samples. So one other thing about Mars that's very interesting is, originally we thought Mars was a dead, arid planet, that it maybe had water long ago, but doesn't have any water now. But there are two findings recently that have been shown by the orbiters around Mars. One is the fact that at the poles, there are these carbon dioxide ice caps. However, below those ice caps are actually some saline water, liquid water, that is probably about size of a sea or so. In addition, those orbiters have found a water table on Mars, meaning that there is presumably water below the surface on Mars throughout the rest of Mars. So Mars may be liquid more than we think. And if that's so, it's possible that it could harbor life now. So there are other bodies in the solar system that we have to look at. There's some other planets that might have free water, although they're not in the habitable zone. They don't have enough energy from the sun, but they do have chemicals that are needed for life. Well, how do they get the liquid water, and how do they get the energy? Let me give you an example. Europa is the one we are going to next. It's one of Jupiter's largest moons. We have found from the different probes that have been sent to Jupiter and its moons that it has this ice crust that's several miles thick. But below that ice crust, there's about twice the size of all Earth's oceans combined as an ocean on Europa. It's way out of the habitable zone, but it clearly has energy because it has this liquid ocean. That's the only way that it could have a liquid ocean, if there's energy. In addition, there are plumes of ocean water spraying out that have been seen. And again, that requires a great deal of energy. It also does have a rock mantle, as well as a probable liquid mantle with plenty of minerals needed for life. Well, this is the surface of Europa, and you see most of it is like this white ice, but there's all this other material that's been deposited on the surface because of these plumes. And that's likely organic material, that is carbon-based material. And this is a sort of a depiction of what Europa looks like. There's a core, then this mantle, some of which is liquid. The area closest to the water is liquid. This ocean that basically is throughout the entire planet, and then this ice crust. To think of it in another way, these are comparisons. This is, let's say, Earth. We have known life, but all of Earth's water is this much. We're not a water planet. We're a rocky planet. We have water on it, and a lot of water, but but that's not what the planet is mostly made of. On Europa, you see that not quite half the planet is water. And this is how basically Europa gets its energy. As it goes around the planet, it has an elliptical orbit. And so as it orbits Jupiter, it's pulled and compressed. And that causes a great deal of friction internally. It heats up the mantle, which also heats up the water. And that's how you get liquid water and liquid mantle. Now, there's something special about that liquid mantle also. And that is it forms hydrothermal vents. Now, this is on Earth. These are hydrothermal vents down at the bottom of the ocean, 3-4 miles down, where there's no light, no heat, no energy. It's near freezing, but there are these hydrothermal vents coming out from below. And you see there's an abundance of life around these hydrothermal vents. You can see all these shrimp-like things and clams and creepy crawly things and all kinds of stuff down here. And the hydrothermal vents are coated with algae. Now, the interesting thing about this is that when these samples have been taken and looked at, and when they look at those samples, they find that there's a large number of different species, but some of those species have absolutely no connection with any other species on Earth, meaning that they formed down in those hydrothermal vents at the bottom of Earth's ocean. There's clearly a message there. If that can happen, why not on Europa? There's some people even thinking that perhaps these hydrothermal vents were not as deep before. And that's where actually life first started on Earth, not in these tidal pools that a lot of scientists thought. Well, what NASA's going to be doing is sending a spacecraft called Europa Clipper spacecraft to Europa. And that launches next year. It's going to do 50 orbits between Jupiter and Europa to avoid the radiation. But it'll do 50 flybys of Europa, including hopefully going through those plumes of water to be able to detect what the ocean is like. I had the pleasure of being able to see Europa Clipper being put together in the Jet Propulsion Laboratory. It's very large. Just to give you an idea, this is the clean room, which is massive. And this is Europa being put together. It's about maybe 12 to 15 feet tall. The solar panels that go with it, these will be probably about 50 feet across or so. So it'll launch next year. It'll take 6 years to reach Jupiter. And then it will orbit Jupiter with swings around Europa because of the high radiation. So it'll do those 50 swings over 2.5 years. And its goal is to determine definitively habitability. It's not meant to determine if there is actual life. My hope, though, is that if they find biologic molecules in those plumes of water, that there's a good suggestion that would be the case. But looking also at the consistency of the ocean by radar and spectrography of the plumes of water. And it'll look for possible sites for future landers and rovers that could actually burrow in and take a look to see if there is life there. If you're interested, the National Poet Laureate wrote a poem about Europa, and the Europa Clipper, and that's being put on a little disc that'll go on board the spacecraft, and anyone who's interested can sign their name to the poem, which I did here, as you see. And all you have to do is go to that website, or if you just type in NASA message in a bottle, you'll get there. And if you're interested, you can have your name going around Europa. Now, another moon is Ganymede. This is Jupiter's largest moon. It has a huge ocean underneath the ice shell, much bigger even than Europa's, and it also does abut rock. And again, you see the outside looks like just a bunch of ice. You notice there isn't any of the coloring on Ganymede like there is on Europa. And the reason for that is there aren't any plumes of water coming out. The shell is dense enough that it doesn't allow for plumes of water. And that may be one problem with it. But you see, the ocean is much, much larger here in Ganymede than it is even in Europa. And again, has a liquid core, probably of iron, and then mantle, which is probably hot. And again, there's whoever's speaking, if you could mute yourself. Thank you. Basically, the tidal heating that we saw the other time with Europa probably is going on with Ganymede as well. Another interesting moon further out is Titan, which is Saturn's largest moon. So we're the next planet out, and much, much, much colder. We're now far beyond the habitable zone. But it's similar to Europa in some ways. You can see the difference between Earth and Titan. Earth and Titan both have nitrogen atmospheres. The pressure is not that much different. The temperature, average temperature on Earth is 77 degrees Fahrenheit. The average temperature on Titan is minus 289 degrees Fahrenheit. So quite a big difference. We have a liquid cycle of water. So we have oceans and lakes and streams. The water evaporates from those oceans, goes up in the air, forms clouds. They get heavy and they rain, and the water comes back down. And that's the liquid cycle we have. Titan has the same liquid cycle, but instead of water, it's liquid methane that is raining. The surface rock that we see is all silicon dioxide, quartz, sand, all those kinds of things. The surface rock on Titan are organic compounds. So carbon-based compounds form the solid rock. And then the crustal rock, meaning the underneath the surface, again, we have silicon dioxide, whereas Titan has water ice as rock because it's so cold there. But there is an atmosphere. Titan has organic hazy layers, and it's like an atmospheric organic factory. There's all kinds of organic molecules up here being formed. And this is an artist's conception of Titan looking back at Saturn with methane rivers and lakes and seas, and this surface rock being organic material. The thing is, if you look at it, though, there's another layer of water. This is an ocean below the surface on Titan, again, because of tidal heating. But given the fact that this has such an organic rich atmosphere and an organic rich surface, all of that can penetrate into the ocean, sort of setting up the possibility for life forming down here. And so that is one possibility also, besides Europa and Ganymede. One thing to also note is that microbes will live anywhere they possibly can. These are some tiny ice crystals from the Arctic. They're very, very tiny. And they're in these ice crystals is a tiny, tiny drop of water. And you see when you use a fluorescent stain, these are two small bacteria in that little tiny drop of water. So life may be around us a lot more than we think. Enceladus is another one of Saturn's moons. It's one of the smallest moons. This one orbits closer to Saturn than Titan does. And it does have geysers with ammonia-rich water. Again, looks like an ice planet, okay? But we know this is an artist's conception, but we know we have seen with Hubble and some of the other telescopes, as well as with the Cassini probe that went there, that this ammonia water sprays out. Well, ammonia water, yeah, okay, and it probably has an ocean, okay, but ammonia water doesn't make life by any means. However, there's a couple of things. There's the Cassini probe looked at those plumes of water with a spectrometer, found there were large amounts of dihydrogen, which is evidence for hydrothermal vents like Earth's. There's an abundance in the atmosphere of carbon dioxide and methane. And in the plumes of water, there are new findings of phosphate. Phosphate, for anybody who might remember their biology, first of all, is part of DNA, but more importantly, is involved in energy transfer in cells. So that's how energy is stored and transferred and used. Well, if you're using energy in that kind of way, it's a suggestion that there could be life there, and that's why it's present. So NASA does have plans for a flagship mission sometime in the future, maybe about 10 or 15 years from now, called Enceladus Orbilander, where one part of the spacecraft will actually land on Enceladus, and the other will continue to orbit and evaluate those plumes. Another moon is Callisto. This is the second largest of Jupiter's moons now. Originally thought to be a dead world, just frozen in ice and rock. Later probes demonstrated the possibility of the ocean, but the ocean is either deeper than was thought, or it's not present and it's just like slushy ice. So this is Callisto, but we're not really looking there for any suggestion of life at the present time. But you do see there's possibility of this thin ocean, either ocean or slushy mix, again, because of the tidal heating. Uranus and Neptune are the two smallest gas giants. They're both about the same size. They're the furthest planets in the solar system, so obviously the coldest. They've only been visited by Voyager 2 in the 1970s, so we don't know much about them. We do know they have, like Uranus has these moons, Titania, Oberon, Umbriel, Ariel, and Miranda, but we don't know anything about them. So is there possibility of oceans and life? We don't know yet. These are things that will have to be explored in the future. So if you look at comparisons of different worlds, Enceladus, which is the tiniest one, has an ocean that's about half or more the entire composition of the moon. Earth, as you see, is really tiny in terms of the amount of water it has. because it's mostly rocky. And then you get to Europa, where it's maybe a third or so. Pluto and Triton, where it's a half or more, but this is mostly ice because it's so far out. Callisto, again, large, but might be mostly ice. Titan and Ganymede, especially, are moons that basically could conceivably harbor life. And then the question becomes, could there be life on Venus? Now you have to remember that the temperature on Venus is 900 degrees Fahrenheit. The reason for this isn't that it's so close to the sun. It's not. It's in the habitable zone. The problem is that there was basically a runaway greenhouse effect, and that may have been started because of volcanic activity on Venus. So there was lots of carbon dioxide and sulfur dioxide thrown into the atmosphere, and it clouded the entire planet. And that works like a hothouse effect. That is, light, UV, infrared, can penetrate those clouds and heat up the planet, but it can't radiate anything out. So it keeps on heating. So the planet is about, on the surface, is about 900 degrees Fahrenheit. So, and the pressure on that surface, because it's such a thick cloud, is 90 times that of Earth. And the clouds have sulfuric acid. So there is no life on the surface of the planet. But there's some suggestions that maybe there's something in the clouds. Early Russian probes found particles in the clouds that were about a micron long, which is about the same size as bacteria on Earth. So they could be bacteria, but they could also be just inorganic or organic compounds and clusters. And most scientists agree that that's unlikely that they're actually those bacteria. US orbiters found dark streaks in the clouds. They persist despite 200-mile-per-hour winds. And they originally thought it could be just organic material or mats of bacteria. Now, mats of bacteria would be startling. But again, they think that it's more just reflections of the underlying mountains and stuff that are on Venus. The most important discovery recently has been the discovery of phosphine in the clouds. Now, on Earth, phosphine is a byproduct only in some industrial plants, and clearly there are no industrial plants on Venus or bacteria. So the question becomes, could bacteria be floating in the clouds? The way it would work is in little water droplets that were in the clouds, these bacteria might be harbored, and no one knows for sure. So in summary, we don't have evidence of intelligent life yet. But there are so many planets in the universe, it's actually likely there is intelligent life somewhere else. It's just a question of whether we'll ever find it, because how far away it might be. There's no definite evidence of any life in our solar system. But many planets and moons have habitable conditions. We now know there's at least one exoplanet around another star that has a habitable condition and possibly a biosignature of life. So that's a possibility. There might be some possible evidence of current life on Venus, and that will eventually be explored with some probes. And so the conclusion is that, at least in my mind, is that we're likely to find life within the next 20 years or so, with more probes and more investigation of all these different moons and planets. And with that, I'll stop and leave time for questions.